So welcome to tonight's Pagel's public lecture. It's the 8th in the series. There are 3 more, and I won't use the time to tell you about the other lectures, but you can look at them on the back of the program. And there's also a stargazing activity next week. Tonight's lecture is going to be really cool. It involves fishing for neutrinos. How many people have been fishing for neutrinos? Only a couple. Okay. But how many people have been fishing for neutrinos at the South Pole? The speaker tonight is Francis Halzen. He is the Gregory Brett and Hilldale Professor of Physics at the University of Wisconsin at Madison. Now, Francis was born in the Flanders region of Belgium. I learned that Belgium is actually a country. Oh, you were supposed to laugh, Francis.
I did.
And he received all of his degrees in Belgium at the Catholic University of Louvain. And it's interesting, the year he received his PhD, you know about Belgium, they've got the 2 different languages, and it's a split country and all of that. And the year he received his PhD, the university split into 2 universities. And is that right? Did I get that right? Yeah. Yeah, the French one and the Dutch one, and he's more associated, I think, with the Dutch one. Is that right? Did I get that right? Okay. And it's one of the oldest universities in Europe, and in 10 years they will be celebrating their 600th anniversary. Now, Francis was trained as a theoretician, you know, the hand wavers, the ones who actually don't do any work, and of course this Aspen Physics Center is all about the theorists. But he got a brilliant idea, and to get it done he had to dirty his hands, and he's been working at the South Pole since 1987. Although one question I think you should ask him, because I can't figure this out, is how many times he's actually been to the South Pole, but I'll leave that for you to ask. What he's going to talk about tonight is a discovery that Physics World magazine in 2013 called the Breakthrough of the Year, the discovery of neutrinos from outside our solar system. And I thought I would just give you a little bit of sense of Francis, who's not only a terrific physicist, but a very interesting person. So, of course, I went to rate my professor, and so here's the first one I found. Really awesome professor with a fun accent to listen to. So you're all going to get to experience that tonight, and I would agree with that, actually. I do enjoy listening to Francis talk. Physicists rarely say that about other physicists. He definitely knows what he's talking about. Now, that's very important, because you guys have just invested an hour in this, and makes class really interesting with funny remarks. So I want a volunteer. Would you volunteer to count the number of funny remarks, and we'll keep track of that. He was interviewed in 2010 by Seed magazine, and I really like this because my wife will know why I really like this. He was asked, you know, when you were a kid, what did you want to be? And he wanted to win the Tour de France. And of course, probably when you were a kid, Eddie Merckx, was he? Yeah, the great Belgian rider. He was recently honored a couple of times in Belgium with an honorary degree and something called the Franke chair. Did I say that right? And so there was a very nice article about him, and I bet if I read this in Dutch or French it would even be better, but I think it sums up what he's going to talk about tonight and his accomplishment. And it goes like this. He is the theorist who had the misfortune of devising a brilliant experiment. And that's this turning a cubic kilometer of ice into a neutrino detector. I think it must be the biggest physics experiment anywhere. Is that right, Francis? His Belgian persistence, and that sounds good. I think there's a story behind that. I didn't know Belgian led to its construction, and I know a lot about this experiment, and it would not have happened without Francis, and it took an enormous amount of persistence to do. And here, this is a direct quote from him, and this is to pique your interest, and then I'm done and he will talk. He said this experiment that he's going to describe tonight, with it, we will solve the mysteries of the universe. I give you Francis Halzen.
Thank you, Michael, for this very nice introduction. In fact, to counterbalance it, I remember when you mentioned my accent. I had just arrived in the United States, and I met Marty Bloch, who is sitting on the first row here. And we started working together, and at some point he said to me, Halzen, he said, if you didn't have an accent, nobody would take you seriously. Today about ice and neutrinos. So if you came to see nice pictures of Antarctica, like this one, you're in the wrong place. In fact, this is a picture now that I have it of Frank Hurley, who was the doctor in the Shackleton expedition and made these beautiful pictures. There will be no penguins today. In fact, this is the place where I have never been, but someone brought me a picture of it. This is the South Pole. It's a desert. There are no animals. There's no vegetation. There's nothing. The interest is that you stand on 3 kilometers of ice. And so that's what this is about. And in fact, we have changed the South Pole a little bit. That thing is there now. And you are not looking at IceCube. You are just looking at 2 floors of computers. IceCube is actually a mile deep in the ice. So to explain this experiment, we'll have to go through a long list of things I have to explain. This is the list. So strap in, is going to be a rough ride. I'm going to explain what a neutrino is, what cosmic rays are, because they play a role in this story, then what neutrino astronomy is, then what IceCube is, and then you get rewarded. You see the first. And I'll tell you about the first surprise we ran into. So what's a neutrino? Well, when you went to high school, you probably had a lecture sooner or later that explained that the whole world is made out of protons, neutrons, and electrons. Protons and neutrons make nuclei, and nuclei with electrons make atoms. Well, if that's what they told you, you didn't get your money's worth, because that world wouldn't exist. So the reason is that neutrons can change into protons. That's called nuclear physics. And so people discovered this, and they noticed that, for instance, the neutron can decay into a proton and an electron. And so what they occasionally would see, if I am the neutron, then the proton would go this way, the electron that way, and that's impossible. That's also high school physics. That violates momentum and energy conservation, this billiard ball physics. Something has to go that way. And the something that goes that way is the neutrino. So without a neutrino, there is no nuclear physics. Is that important? Well, without nuclear physics, the sun wouldn't shine. It's a nuclear reactor. Without nuclear physics, most of the stuff you and I are made of, the oxygen in this room, was born in the explosions of stars. It's when nuclear reactors run out of steam. So neutrinos are pretty important. They are the agent that make nuclear physics possible. And so one of the reasons, I can tell you right away, to look for neutrinos in the sky is that they will track interesting regions where nuclear physics is happening in the universe. So this proposal actually was made by a man named Pauli, a theoretician, and so this neutrino was a particle that had no mass, didn't interact with anything, It was just invented to save energy conservation, which is a basic law of physics. And so he said, I have done a terrible thing. I have invented a particle that cannot be detected. And I remember over the years when we were trying to build IceCube, I would often tell my colleagues, we're going to prove him right. This is what the world is made of. Now, this is kind of a cliche in these talks, and I used to leave it out, but I brought it back in this slide, this poem by John Updike, who fortunately died a few years ago, because he said all the right things about neutrinos in a few lines. Neutrinos, they are very small. They don't have electric charge. That's critical. Because a particle that has an electric charge, you cannot do astronomy with. That is really the most important property. You know, we detect protons from the universe, incredible numbers with high energy. But we live in the galaxy, and the galaxy has magnetic fields. The proton has a charge. So its path, from wherever it comes from, is bent by the magnetic field in the galaxy. And so if you detect a proton coming from there, it may have been produced somewhere there. So their path is scrambled by magnetic fields. So the next thing is they have no mass. That's not true, but it's true in this talk. Mass of neutrinos, they have a tiny mass, but in this talk it's completely irrelevant. They do not interact at all, and that's true. Because they have no mass, they are actually no electric charge. They're just like light. A stream of neutrinos is like a light beam. There's really no difference. Except for one thing, neutrinos go through walls. Light doesn't go through walls. And that also makes it interesting because they don't interact with anything. They go through the Earth, they go to planets, they go to everything. And so the hope is you can do astronomy with them. You can like look closer to a black hole where light can never escape. So that is the best introduction to a neutrino that I can think of. In fact, they never show you the second page of this poem, which is very nice too, but it's slightly pornographic. Now everybody is going to look it up, right? So neutrinos were created in the Big Bang. They are created when stars explode. I already mentioned that. They are created by the sun, wherever there's nuclear physics, nuclear fusion happening. They are created in the Earth. There are radioactive elements, thorium, uranium, in the Earth. This is a nuclear reactor. This you should pay attention to. Notice this is a nuclear reactor, and what you see, this blue light, it's the reactor is covered with water to shield the radiation that comes out of it. And this blue light is the particles that travel through the water, like electrons. They emit this blue light. This light will play a big role in this talk. So you emit neutrinos, quite a lot actually, because the potassium in your body decays. And we make neutrinos at accelerators. So neutrinos are everywhere in enormous numbers. You know, I could now go to the spiel where you mention billions and billions. I won't do this. But in this talk, there is another place where neutrinos are produced. Neutrinos are produced continuously about 20 kilometers above our heads. And the reason they are produced is because cosmic rays bombard. Cosmic rays are I already mentioned that protons bombard the Earth. This was discovered in 1912 by Victor Hess. And so these neutrinos, these particles, bombard the atmosphere. They interact with nitrogen and oxygen, and they make pions. And these pions decay in muons and neutrinos. And these neutrinos then come down to the Earth. And so if you look at the sky, you see neutrinos being produced continuously. But they are produced by, we understand how they are produced. They're kind of boring. They're called atmospheric neutrinos. There are actually 110 neutrinos, I'm not sure this number is right, per cubic centimeter left over from the Big Bang. And the fact that the universe is filled with neutrinos is very important. This is the universe. These filaments is where the stars are and all the stuff we see when we look up to the sky and where we live here, this red dot. And you see the universe would have been very different without neutrinos. So neutrinos are important particles. So I hope you are now sick of hearing about neutrinos. I already mentioned cosmic rays, but now I have to introduce cosmic accelerators. This man detected the cosmic rays that bombard the atmosphere. He's Victor Hess, an Austrian physicist who actually ended his life in New York. And in 1912, he went to 17,000 feet, and he saw the radiation in his detectors increase. Notice he went to 17,000 feet with oxygen, but with his Sunday suit on. And we have actually detected cosmic rays of 300 million TeV energy. Now, what's a TeV? A TeV is a unit of energy. And it doesn't matter what it is in detail, but the biggest accelerator in the US produces an energy of 1 TeV. It's at Fermilab near Chicago. And so the energy of the biggest accelerator is going to be the small unit in my talk, 1 TeV. So we have seen protons of 300 million TeV reach the Earth. And we have no idea. So we know about this for more than 100 years. We have no idea where they come from, how they are accelerated. And so, but of course, theorists theorize. And so the idea is that maybe in the galaxy some are produced when stars explode. And there are ideas that about extragalactic, there are galaxies that have enormous black holes at their centers. We have a black hole at our center, but it's a very wimpy one, 100 billion solar masses or so, and that somehow these black holes produce the power to accelerate these particles. But you realize in this type of places, neutrinos must be produced. And so the goal of neutrino astronomy is to look for these accelerators with neutrinos. In fact, we know accelerators exist because this is a solar flare. And when what you are looking at, these filaments are streams of charged particles. Now, when a charged particle moves, it makes a magnetic field. So there are magnets there that can accelerate particles. And in fact, when a solar flare happens, we see protons arrive of 10 GeV. That's 1/100th of a TeV. Compare that, so this 1/100th of Fermilab, not 300 million, but it's an accelerator. So this is an accelerator we kind of understand, but it cannot get us to high energies. And so we invent magnetic fields and systems that can get you to larger magnetic fields over bigger distances. And so this is an exploding star in our galaxy. This is a star somewhere in the universe that collapses to a black hole. And these are the systems, the galaxies with supermassive black holes I mentioned before. So these are the things, this is theory. So these are the things we are going to try to prove. So eventually, by the end of the day, we have to tell where this cosmic ray came from. Now, I won't spend much time on that, but if you wanted to build an accelerator, which means lining up magnets to produce this cosmic ray, you would have to fill the orbit of Mercury with magnets continuously. And so somehow nature managed to do this. And so it certainly, you would agree, it would be fascinating to find out. And so the reason we believe these objects produce neutrinos is very simple. We have something at Fermilab and at CERN in Geneva that's called a beam dump that produces neutrino beams. What you do is you take the accelerated proton beam and shoot it in a target. You produce particles that decay, like pions, that decay in neutrinos, and out comes a neutrino beam. So you see, in the concept of accelerators that I described to you, you see there are collapsed objects like black holes and neutron stars that kind of provide the energy for the acceleration. But these objects are surrounded by light, by dust, by molecules. And so the protons, when they leave their accelerator, they also interact with a target just like at Fermilab and produce neutrino beams. These are the ones we want to look for. So I think I've already introduced the concept. So you want to have a neutral particle. It's essentially massless. So it's just like a photon, except it goes through everything. But this is a picture taken by the Hubble telescope. And you see it's visible light. It's better than your eyes. But this is a star that exploded in 1054. If you look at this star in different wavelengths, you can think of different colors. You see, this is the same object. And you see in each of this is, well, you see them listed. And you see, you wouldn't even guess this is the same object. So whenever you look at the sky in a different way, you see new things. In fact, it's only in the last decade that we discovered this beam of particles that's coming out of the center of this object. Was never seen before. And so the astronomers have been good at this, and they have kind of used up all the wavelength of light. So the only thing left to do now is to switch particle and to try to look at the sky with neutrinos. And so that's the other motivation to build an instrument that can act as a telescope to look at the sky in neutrinos. And so I was always trying to sell this project, as Michael said, this was not easy, by showing this table that comes out of an elementary astronomy text, and which has actually terrible history in it, but doesn't matter. The point of this table is that whenever you have a new way to look at the sky, you actually don't see what you're looking, you don't find what you're looking for, which in our case is cosmic accelerators of cosmic rays. What you actually see is something always much more interesting. In fact, you talked about Flanders. The optical telescope actually was developed first in Flanders, and they developed it to look for ships coming from England. If you had the strongest telescope, you could sell what was on the ship first. So they were making money. There's no evidence they ever pointed it at the sky. But when Galileo heard about this, he knew optics and instantly built one with 2 lenses that was 30 times bigger, and discovers the moons of Jupiter, looked at them, many other wonderful things. And so this list goes on and on. And so what you want to do is join this list. However, one day I showed this to someone who was working for the Office of Management and Budget in Washington. If you don't know what this is, consider yourself lucky. And he said, you shouldn't show this, because what it looks like is that you are asking for money from the taxpayer and that you're going to gamble with it, which is kind of exactly what we were doing. I say, what do you suggest instead? And he said, which of course said exactly the same thing. So there are administrators in Washington with a sense of humor. So theorists have been working out how many neutrinos are emitted by these objects that I've kind of been speculating about for decades. And so they have agreed after a long time that to do astronomy you need at least a mirror that's 1 kilometer square in size, 1 kilometer on the side. Now you don't detect neutrinos with a mirror. It means you have to build a particle detector that's 1 kilometer cube inside. And so how to do this? was suggested by Markov. He actually couldn't even imagine kilometers cubed, but he suggested an idea that we ended up using. And so it's explained on the next slide. So what you do is, his suggestion was, you go a few kilometers deep in the ocean where the water is dark and clear, you fill it with sensors that can detect light. And then you look for the following. I'll tell you in a minute how you detect light. But so you look for particles coming through the Earth. So neutrinos are the only particle that can come through the Earth, and most of the time they just go through the Earth and through your detector. But about 1 in a million times where we are at the energies we are working, a neutrino will interact. It will make a small nuclear explosion and produce electric particles that you can detect. Neutrinos are neutral, you never see them. And so they do that by interacting with a nucleus in the atom of the water. And so they make a small nuclear reaction. And if it's a muon neutrino, they come actually in 3 flavors, which is not that important. If it's a muon neutrino, it will make a muon. Remember, muons were also made in the atmosphere. And these muons travel through the water for kilometers. And so if this thing comes to your detector, you know it has been made by a neutrino because muons don't come through the Earth. It radiates light. It's a charged particle. It radiates light, the blue light you saw on top of the reactor earlier. And in fact, it goes faster than the speed of light and makes a shock wave, a bow wave. And so from mapping the bow wave, you can reconstruct the direction of the muon and the neutrino. And so each neutrino is a dot in the sky above Madison. So from the South Pole, you look at the sky above us. And so each neutrino, think of this as a map in pixels, and each neutrino we detect is 1 pixel in the map. And so let me now, the only physics that go into it is the following. This is how you detect light. It's, it looks like a light bulb. It's this big. It costs $1,000. You buy it in Japan. And it's, when light strikes it, it makes a little electric current that comes out at the other end. So it's the opposite of a light bulb. You put the electricity in, the light comes out here. This works the other way around. It's the size of a basketball, costs about $1,000. So that's the simple part. So these are the light sensors you put in the water. So the blue light made by the muon and other particles is just the same light. These are charged particles coming out of the reactor. In water, they make blue light. And so why was this blue light in a shock wave? That is the last thing I have to explain, but it's very simple. This duck goes faster than the speed of the waves in the water. So it leaves a bow wave behind. It's like a speedboat. And so that's what we refer to as the Cherenkov cone. That's what makes this triangle. So the muon actually goes through the water at a speed which is faster than the speed of light inside the water. And so that's why it makes this shock wave. So that's are the 3 ingredients. And this is the method we use to do this experiment. So this experiment was tried. There was a heroic team at the University of Hawaii. They worked on this for probably 25 years. They tried to put photomultipliers in light sensors 4 kilometers deep in the ocean off the coast of Hawaii. And unfortunately, this is one of their sensors. Unfortunately, this experiment failed. But I want to emphasize this, they invented a lot of the basics of how to build this detector. And the only idea we had was to do the same thing. We actually realized that why they failed and concluded that it would be easier to put light sensors in ice than in water. And that sounds crazy, but history has proven us right. And so, but to our credit, we realized this. So this is the South Pole, the geographic South Pole. This is the South Pole Station. So the luck we had is that it so happened that the National Science Foundation had developed this beautiful infrastructure at the South Pole where it's actually possible to do an experiment of this size. I mean, if that hadn't existed, there's no way we would ever been able to do the experiment. That's the IceCube Project, and this is the runway where the planes land. Everything that comes to the South Pole comes from Christchurch, New Zealand, to the coast of Antarctica, McMurdo, and then goes by C-130 or similar planes to the South Pole. So everything you ship to Antarctica has to fit in a C-130, which is part of the challenges of this experiment. So I like to show this picture. This was 1993. By then we had been thinking about this experiment for several years, and so we decided we were going to try this. We actually got a grant from NSF. This is a long story I don't want to go into, but NSF actually gives grants for ideas that are so crazy that they cannot be reviewed. And they give you at the time $50,000, and then you can prove your idea, and you cannot come back if it doesn't work. And so I was a theorist, of course, so I didn't have a lab. But the theory group had a ping pong table, and so we removed the ping pong table and changed the room into a lab and built these modules. This is just a photomultiplier in a pressure vessel. And so, in fact, I should introduce these people. This is Bob Morse, who's now retired, living in Hawaii. This is Serap Tilaf, who's a professor at the University of Delaware. And this man is Igor Liobarsky, who transferred from the University of Illinois because he wanted to work with me on QCD. And so I told him, well, now you're going to build optical modules. And in fact, he did very well. He's now working on one of the premier double beta decays of the University of Valencia in Spain. In fact, the PI of that experiment is sitting there. So what we did with the money is put, and some more, is put 750 of these centers about a mile, 800 meters from the South Pole. So if you go under 800 meters from the geographic South Pole, it's there. In the year 2000, we had put 750 of these. And you see this is the electronics at the surface. And so we managed to see neutrinos. This is one of the first neutrinos ever detected. So what you are looking at is this muon track, so muon track coming through the Earth. And as it goes through the Earth, so the light, this is the online display of the experiment. So each of these dots is a photomultiplier tube. And so the way this display works, I will show you more, you follow the colors of the rainbow. So red is early, then green, and blue is late. So this comes through the Earth. The size of the ball is how many photons that particular, how many particles of light that particular detector detected. And so this is a neutrino. It's made somewhere in the sky above us in the atmosphere. It's an atmospheric neutrino. No big deal, but that you could build a big detector. By the way, the size of this detector is about 200 meters this way and 500 meters this way. Although it was an R&D project, it was not a small detector. So what do you do? So we detected several hundred neutrinos, and then we knew what to do. You publish in, what was it? Yes. You publish in Nature, and then go and ask for more money. And so the goal was to build a kilometer cube detector. In fact, our original proposal said that we wanted to build a kilometer cube detector, so this was always our goal. You see, the collaboration had grown by then. And we got a break just before asking for more money. We were declared one of the 7 wonders of modern astronomy by Scientific American. However, I showed this in small print because you see this is us, this is the Hubble telescope, and this is us, and the category is in the weirdest telescope. It was not easy to sell this idea because even after seeing it happen, people were reluctant to accept that this method was really a better investment than doing this in water. And the people doing this in water were still kind of struggling, trying to do this. And so another administrator in Washington actually gave me this cartoon at some point. He was trying to point out that we had found the most difficult way to actually detect neutrinos. And that was our problem. We had to convince them it was not. And that's where the idea came from for the title of my talk. So this is IceCube. Now you know what you're looking at. This is a kilometer cube of ice. It's a mile, 1.4 kilometers under the surface, 800 meters. In fact, Amanda, it's not shown, is sitting inside this detector. And it was working beautifully. It worked for 15 years, and we had to turn it off. You know, it wouldn't die. These sensors, between 93 and when we turned it off in 2009, we never lost one of these sensors. It's, you know, unbelievable. Anyway, so this is a cubic kilometer of ice, and it's filled with 5,160 of these photomultipliers. So the same story, bigger. But now, of course, you are desperate to know, maybe not, how we put this stuff in the ice, right? And so what I'm going to do is show you a movie. It's only 2 minutes long, so less actually. So this is the cartoon. The first 90 meters of ice is actually snow, and so you just melt the snow. Then comes what we call a hot water drill. It's just a nozzle that puts out hot water under pressure. It falls under gravity, and it melts the ice as it goes along. So after 2 days, you have, over about the size of your detectors, you have transformed ice into water. And so this is the power plant. So you need a power plant of about 4.8 megawatt to melt the water. And so here you see a movie how this works. All this, everything is mounted on sleds. So this is the drill tower. This is a 2.5 kilometer hose that at some moment hangs in this hot water without collapsing. I mean, this is a marvel of technology. It's a company in Italy who managed to build this. And this is the power plant. It's basically 40 car wash heaters. And these are the generators that supply the power. And you see this is the power plant. All this moves around on the ice on skis. So what happens is, here you see the hot water drill coming out. You see just a metal tube with a nozzle at the end. And then the stuff moves to where you put the next sensors in, which is 125 meters away. And so ready are 60 optical sensors, and they are going to be sunk in this hole that's now water. There's never a hole, actually. And you will see here, this is the electric cable that brings down the high voltage. And the signals from the photomultipliers are digitized in the ice and brought back over the same cable to the computers at the surface, which you saw in one of my first slides. You realize, of course, after a few days this hole refreezes, and it's like launching a satellite. You never see your equipment again. You cannot repair it. And so the way, if you could go down in the ice and look at this detector, what you would see is, you know, every 17 meters for a kilometer, you would see these light sensors. And if you look 125 meters away, you would see another string like that. We did this 86 times without any failure, and that was IceCube. So this is a cartoon, again, of what we're doing. This is a muon traveling through the detector. You see the blue light emitted, and you see the light sensors lighting up, and you don't need a computer to see the direction of this muon. Of course, this one didn't come through the Earth. This was one that reached us from the atmosphere. So I want to actually show you, I cannot resist, IceCube in action. Remember, the atmosphere emits neutrinos. In fact, while I'm talking here, IceCube detects a neutrino every 6 minutes. It detects the muons that come from the wrong side through the detector. And so we want to detect, so we detect muons made in the atmosphere in the back of the detector. We see neutrinos produced in the atmosphere everywhere on Earth, right? Because they go through the Earth, so we don't have to look above. We see them from everywhere around the Earth. And so in this background, we are looking for neutrinos that come from the cosmos. So here you see the detector taking data. So each time a photomultiplier, each time a sensor detects one or more photons, it sends a message to the computer. And you see we collect these messages on the computer and then build them into neutrino events, which overwhelmingly means muon tracks. And so you see these muon tracks being continuously reconstructed by the computers. This is a big bundle of cosmic ray muons going through the detector. You see the movie repeats itself. This movie is 10 milliseconds long. So what that means in practice is that we detect 70 billion neutrinos muons per year. About 100,000, in fact this number is too small, about 100,000 atmospheric neutrinos, one every 6 minutes. In fact, we detect 3,000 muons per second. So almost everything you saw in this 10 millisecond movie were cosmic muons. We have no cosmic ray muons. We have no interest in. And in this mess, we have to find 10 to 100 interesting neutrinos. And so while we were building the detector, we, for instance, found this event. And it has an energy of almost 100 TeV. Remember TeV, the energy of the Fermilab beam? It's 10 times the energy of the LHC beam packed in a neutrino. And so this is interesting because this energy is so high that you have to doubt whether the atmosphere can really produce this event. But we were not sure. This was intriguing, but we convinced ourselves that it was consistent with being an atmospheric neutrino. And then I remember sitting on a Thursday 3 years ago in a boring routine conference call, and someone showed this event. You can enjoy it with me. Here you see light starting, and the light moves up and down the string. You wait for a while. You light up all the strings around it, 125 meters away. You wait a bit longer. You get more of these. Now this event we figured out. In fact, we had practice looking at this. That's why we were so, we've never seen something this big. In fact, basically, the size of this light pool tells you the energy of the neutrino. And by then we had looked at so many of these events, we immediately realized we had never seen anything like this before. In fact, in the analysis that generated this event, there was another one, which has exactly the same energy. And I have to remind you now how big this event is, because that's important. This is the event superimposed on the data center in Madison. The way this experiment works, the data are analyzed in this 2-story building you saw in my first slide. Then it's sent by satellite to New Mexico, from there to Madison, Wisconsin. There we have bank of computers that further analyze the data and turns it into science data that we send to a collaboration of, by now, more than 40 institutions all over the world. But you see the size of this event, and what this event actually is not, you saw no muon track, right? That was the spectacular thing. What it actually is an electron neutrino, and so an electron neutrino interacted inside the detector. It makes no muon, but it makes charged particles, and these charged particles then shower in the ice, and they emit all kind of Cherenkov light as well. But this showered is a source of light that's smaller than this room. And in a kilometer cube detector, that's like turning on a light bulb. It has no size. And so that's what you saw. You saw a light bulb being turned on. But fortunately, and so you would think, well, this is not astronomy. You cannot reconstruct the direction, but we can, because I'm going to show you, this is a computer simulation of this event. And you see the light bulb being turned on, but look at the color. Red here, yellow there, now yellow here, blue there. And remember, color is time. So it means this electron actually came in from here, and the photons that arrived at our sensors there arrived earlier than at the sensors there. And from that, we can reconstruct the direction. So anyway, here are these 2 beautiful events. We published them. We didn't claim anything. The probability that this was a real detection was like 3 sigma. It doesn't matter what sigma is. It's where you get excited, but you are not sure yet. So, in fact, some people get excited at 1 sigma. Right? So here is what we did. We looked just for more events starting in the detector. That means we ground through all our data, requiring that no light enter the detector. So for instance, here is a neutrino that interacts. It makes a muon. When you look back, no light enters, nothing enters the detector. And so that's a neutrino, but it starts in the detector, and you can contain and measure all its energy. And so when we did this analysis, in the same data, we discovered 26 more events, and you now know the rule. You publish, this time in Science, and you go and ask for more money. In fact, this was declared the Science Breakthrough of the Year by whichever magazine does this. Now, I have to, it's always talking about missed opportunities. New Scientist had this webpage. I mean, this is not a joke, this is real. Had this webpage where they actually let you bet on large experiments making the discovery they promised or not. And for instance, here you see Atlas, the LHC. You could bet 6-1 on the discovery of the Higgs. And in fact, our experiment, you could bet 6-1 on the discovery of cosmic neutrinos. You would have won a bomb of money if you had bet on these 2 experiments. However, they took the website down. And the reason they put the website down is they gave gravitational waves and LIGO 500-1. And we started all betting on it, and they got nervous. In fact, for new scientists, you must question this whole approach, because finding Elvis was alive was 100-1, and the Loch Ness Monster 66-1. I couldn't make this up. This is so. I'm almost finished. What did we see? The neutrino sky. And so what we see here, after 4 years of data, these are the pixels on the sky. And so where do they come from? And the first thing is that what you are actually looking for, and for a bit of history, that probably will never be written, the first event we ever measured the direction of came from 1 degree from the center of our galaxy. And you know, I went home that night depressed, and I said, you know, we'll see the center of the galaxy, fills our detector with neutrinos, and that's it. And of course, you see all the other events. Nothing is close to the center of the galaxy. So this is the plane of our galaxy. And so if they came from our galaxy, they would cluster in this plane. There is no evidence for that. This is something we got excited about. But in fact, if you look at our science paper, this was the map of 2 years of data. This is the map of 4 years of data. This didn't grow, so it means this is nothing. And so what the conclusion of this is that we are actually seeing a flux of accelerators, of sources, that's extragalactic, that fills the universe, and is totally uniform. And you know, as neutrinos reach us from anywhere in the universe, they don't, this is exactly what kind of bargain we got what we bargained for. Now, if you remember my picture about, this is a bit technical, so allow me 2 slides, so you don't just listen to it halfway. I just want you to get the idea what's actually surprising what we discovered in this data. So we are collecting neutrinos from sources throughout the universe. And you remember the slide of the beam dump? The beam dump physics works in such a way that for every neutrino you have to produce a photon. This is just textbook particle physics. You know, you have an interaction and you produce pions, and basic physics tells you for every pion that decays into neutrino, you have a neutral one that decays into gamma rays. So no astronomer has seen 1000 TeV gamma rays. So why is this? Maybe this is wrong. No. So we start thinking about this. And so here is the accelerator, whatever it may be. This is the neutrino we detected. This is the gamma ray that comes with it. It has the same energy, it's in a factor of 2. But this gamma ray doesn't get here, because the universe is not an empty place. It's filled with microwave photons, infrared light, everything you can think of. So these gamma rays don't make it to the fog made by all the light in the universe. And so that doesn't mean you cannot see them. What happens is they interact, say, with a microwave photon, make an electron-positron pair. Those radiate more gamma rays. So what happens is they come at Earth, but not as one high-energy gamma ray, but many low-energy gamma rays. And so all we had to do is, and apologies for this plot, so these are the neutrinos. We just had to take our neutrino flux, translate it in a gamma ray flux, dump it in the microwave background, and this is what we predicted the light should be look like. And this is the data detected by the Fermi Gamma Ray Telescope. So the inference of this picture is, unless this is an enormous accident, is that, you know, you build an experiment, work 25 years on it, more in my case, and you finally see a handful of events. You think you would have discovered something exotic or special or abnormal, and actually the conclusion is that we see the same sources, the same universe as in light. So that means that somehow the high energy universe totally works with nuclear accelerators, which will come as a real surprise to astronomers actually. So however, not all in life is boring. See this point here? It doesn't play the game. So there's somehow is something else going on, which by now has a pretty good statistical significance, which we don't understand, and that may actually be exotic physics, we don't know. So this is a story that's evolving fast, and you know, in fact, we were in the news in the last few days because actually we announced that we discovered a record event, which was a neutrino that had an energy close to not 1,000 TeV, but to 10,000 TeV, which again adds to this picture. So what's the future of this project? Well, we made this incredible discovery that light travels through the ice over distances of 100 meters and more. You know, this, if you think of blue light, tap water, blue light will travel about 2 meters. If you distill it, it will travel 8 meters. In this ice, it travels 100 meters. And that's the bad ice. The good ice, 220 meters. And in fact, you know, all these structures here, that has to do with the weather in South America that occasionally puts a bit more dust in the wind that circles Antarctica. And then there is some dust in the snow, and then it's not so clear. And in fact, we understand this in glaciological terms. In fact, we have measured dust in ice now better than anyone else, and I like to show this slide. This is the concentration of dust in the detector. Only, notice this is only between 2,130 and 2,160 meters. So we mapped this dust with resolution better than centimeters, like this. And so you see this here, this is the dust put in the ice by one volcano eruption. And we actually published this. Sometime in my life I wrote more glaciology papers than particle physics papers. And I won't tell you how I felt about that. But so this eruption was 74,000 years ago, and it's a famous eruption. It's a Toba eruption, which someone told me in the previous talk happened in Indonesia. And the geologists saw it in the layers, in the layering of the Earth. They discovered this effect. But the ice cores couldn't see it. And we actually, this was a controversy, we actually detected it here. Just this to tell you, you know, we know more about this ice than we possibly need to do this experiment. And so, but we are continuously improving this experiment with all this knowledge as we get more and more powerful computers and more computers. But so the conclusion is that we can fill 10 kilometer cube with the same number of sensors and have an equally good experiment. Now you say, why didn't you do this in the first place? Well, we actually had an inkling that this was possible. But we had, with Amanda, we had never seen light propagate over these big distances. And if you separated your photomultipliers too far, then you couldn't calibrate the detector. The way this detector is calibrated, these modules have LEDs in it, and you shoot light from one detector to the next. If your light doesn't reach to the next string you cannot calibrate, everything is wasted. And so we were extremely conservative, but now we know what we're doing. So we want to build a detector that's 10 kilometers bigger. So we want to capitalize on this discovery. I won't go into this, but given we see the whole universe, we begin to have an idea of the type of astronomy we can do. And what you really can do with this 10 times bigger detector is hope to see neutrinos, multiple neutrinos from the same direction in the sky, and that's by definition real neutrino astronomy. I didn't talk about this, but the real exciting thing, these neutrinos are never boring. And you saw already one case of this with this bump on our beautiful spectrum that we think we may understand. So they're always things that puzzle you and that often lead to great physics. And so that's why you want to continue to do this. So thank you very much.
Very nice. Thank you very much, Francis. And how many funny comments did he have? Were you counting? 45? Okay, good. And did you like the kind of phony French Belgian accent?
Ask Marty Bloch.
Do we have any questions? Yeah.
So what kind of structures do you theorize the neutrino accelerators may be part of or involved in throughout the universe?
Actually, I mean, some of these...
You're supposed to remember to repeat the question.
Oh, to repeat the question. So these accelerators, we know these accelerators exist, right? And we now see the neutrinos from them. So the question is, how do you imagine, what's the structure of this accelerator? In fact, this goes from wild guess to something we almost understand. So let me give you something we almost understand. And that is the explosion of a star in our galaxy. It makes this picture. So the debris of the collapsing star travels for 1,000 years through the interstellar medium. It builds up these dense shock wave of particles, which I showed in one of my plots. And then shock acceleration there accelerates the particles. And so in textbooks, this is treated like totally understood, and there's no doubt, as I said, or maybe not said, Zwicky suggested this as the origin of cosmic rays in 1933, is that right? The paper, 34. Zwicky, 34, right? Bade and Zwicky. And so, but this is still debated. And so it's still controversial. And if we really see this balance between gamma ray and neutrinos, then we have to see this structure soon. And so that will decide the questions one and for all. We should see, if they are really the accelerators of the cosmic rays, we should see of the order of 10 events in 5 years of data, which we have. And this analysis is in progress. But then, you know, I told you the most conservative accelerator, the wildest one, is that there are cosmic strings in the universe. And cosmic strings, you know, vibrate and they emit, they can accelerate cosmic rays. And so nobody pays too much attention to this anymore. But so, and then anything in between is possible. So, I mean, you clearly need to solve this experimentally because we haven't been able to do it for 100 years. So.
Other question? Yes.
When can you be sure that it detected muons from a neutrino?
Well, the question is, how can you be sure that a muon came from a neutrino interaction? When you see it happen in your detector, you are sure in the sense that there is nothing and suddenly there is a muon, right? That you see that something that you don't see, which is the neutrino, made the muon. You are sure when you see the muon coming through the Earth, because muons travel through the Earth at most a few kilometers. And so if they went 12,500 kilometers, it was a neutrino that made them. So, yeah, I think answers your question, right? Yeah.
I take it that the movement of ice or any possible earthquakes at the South Pole will not affect your experiment?
Okay, the question is, I assume that motion of ice and earthquakes don't affect your experiment. In fact, I remember giving a talk on this at Oak Ridge, just when we started building the detector. And you know, every question on this topic after 25 years you've heard before. And someone in the audience asked this question, and I stood there without speaking for about 30 seconds. And people thought I was sick. I said, no, this is a question I've never heard before. But I was also worried. And then I found out, actually, there are no earthquakes in Antarctica. And if there is one, we are gone. Now, about the motion of the ice is very interesting. The ice, we are sitting in a glacier that flows off the West Antarctic mountain range. And so this glacier moves just over 10 meters a year. So, you know, the earliest photomultipliers have moved over 100 meters. But, yeah, we are trying very hard. This is another talk. I mean, glaciologists have never been able to instrument the kilometer cube of ice and look at the motion of a glacier. So we try very hard. We know where our sensors are to about a meter. And so we try very hard to see for any differential motion. And over all this time, we have never been able to detect anything. In fact, we have one string where in each module there is a tilt meter. And so this ice moves totally uniformly as far as we can tell up to now.
Yes.
You created 10 kilometer cube. Is that realistic with some of time?
Well, it costs the same to first approximation. It's the same number of sensors. It just, and you have to put them in the eye. So you repeat, there are differences in the sense, the thing that doesn't simply scale is that now you have to move your drill over bigger distances. And that's one thing we are worried about in thinking about two drills. Developing this drill was a real headache. You know, where in fact we were told by many companies that this 2.5 kilometer hose couldn't be built, for instance. And that was the end of the project. Because if you cannot do this in a straight shot in 2 days, the project takes much time and you cannot afford it. And so, so we're thinking about going to 2 drills to also do this in a shorter time. But it's mostly repeating the same thing, except for the distance between the strings. And of course, there's now much better and cheaper electronics to read out the light sensors.
So I just want to add,
Yeah.
I can't help but praise the science that's being done down there. So the Antarctica, there was a treaty in 1957. A bunch of countries, including us, had claimed, and nobody knew what to do. You know, I own it, you own it. And so a treaty was signed in 1957 that all the countries would not do military, would not do economic, would only do science.
No tourism.
And no tourism,
No
either,
tourism.
so that would be economic. And so the United States built the South Pole Station, which is an absolute wonder, at a fairly big expense. And at first it was adventure science, and then Francis has told you that it's now world-beating science. So this is the best place that you can build a detector to detect neutrinos or to look for the microwaves from the Big Bang. And so I am betting that since we have all that infrastructure and since we'd like to continue doing things at the South Pole, that's where the hole in the ozone was discovered. And the cooperation at the South Pole is really tremendous. And the U.S. presence, I think this is money as taxpayers we can be very proud that we spent to do this science and to use this continent peacefully. So maybe, is there one last question over here? Or we'll have one more question after that.
Concerning expanding the IceCube, is it infrastructure, I mean, when you're talking, just use your comment, when you're talking the South Pole Station, it's subordinate, doing all the construction and the extra logistics.
Yeah, the question is, that's a good question, especially when I mentioned 2 drills. The limitation of what you can do at the question is, can you do this project, especially with 2 drills, can it be hosted by the capacity of the South Pole Station? And it's kind of, the answer is yes, but this is not a well-researched yes. When we built IceCube, at the same time, they were building the South Pole Telescope, and they were building the new station. And so I would think that 2 drills and IceCube construction with 2 drills is not as challenging as what already done, but that was very challenging. And so, by the way, talking about world-beating science, I think we should mention that your colleagues from Chicago have built this microwave, cosmic microwave background detectors that are also dominating many aspects of cosmology. So this is really, you know, you can think of South Pole as a scientific lab that can compete with anything in the world.
Last question.
You've also already mentioned that the ice is moving. To what degree is the ice eroding, and how does that affect your work?
No, the ice, in fact, I should have mentioned this, the ice is totally stable. You know, the only thing that happens to the ice is that a few centimeters of snow falls on it every year and then compactifies it. And we now know that actually the ice is almost certainly, you heard probably that under the South Pole and in many other places there are lakes. We now know that these lakes are all linked by rivers. And so basically our ice is almost certainly moving on a hydraulic bed on which it just streams.
So Francis is not a skier, so I'll help him with the answer to your question. So the answer to your question is really, really easy. 3 kilometers of base, 2 centimeters of powder year-round.
Yeah, that's what it is, yeah.
How about funny stuff? Do you belong to
Okay, the final question.
300 Club? Do you belong to it?
The what?
The South Pole?
Oh, no, I don't belong to anything. He has been to the South Pole, I have not.
So
Right,
the
you
question
have been,
was
right?
about the 300
Club.
And
He doesn't belong to the
I can only
300
answer
club.
this question for you if you promise that it does not go outside the room. Because this is a completely unacknowledged, illegal club. And since I at one time worked for the National Science Foundation, I'm revealing this. My life is in jeopardy. I have 2 kids. I have a wife. I have 2 poodles. But I really like this audience. So the 300 Club. During the winter, you're stuck down there. During the right now, which is the South Pole winter. So they can't figure out what to do. So somebody came up with the clever idea of the 300 Club. So the 300 Club is you take your body from 200 degrees Fahrenheit, from a steam room, a sauna, and then you go to minus 100 Fahrenheit outside. And there are rules, you're almost naked, and I'm not allowed to tell you the rules. And so you go in the sauna, you run out the door, you take 1 roll in the snow, and you come back in, and then you become a member of the 300 Club that does not exist. So I don't want anyone telling the story, and if you tell the story, Francis will... So
No, I
Francis.
know a lot of people, physicists, but you expect physicists to do this thing, right?
So a change in temperature of your body, 300 degrees. So
I
let's
don't,
thank
yeah,
Francis
thank
for a
you very
wonderful
much.
talk.
Thank you.
Thank you.